In this video, we'll be looking at the domain of algebraic functions. Each operation that shows up in algebra potentially has restrictions. There are two that we're going to focus on. Division cannot involve dividing by 0. And so we have a restriction that the divisor is not equal to 0. Even roots, like square roots or fourth roots, also have a restriction. The input to the root cannot be negative. What we'll do when we have a function is we'll look for one of these two operations. And if there's division, we'll create an inequality that says the denominator cannot equal 0. If we have a root that's an even root, we'll create a restriction that requires that the input of that root has to be greater than or equal to 0. And then the domain will be the set of values for which all of the restrictions for the function are satisfied. We have three functions that we're going to look at as examples for finding the domain. And so what we'll do to start is we're just going to write down the restrictions that each function has. Our first function, f of x, only has division. And so we will create an inequality that says the quotient, the denominator, of that quotient cannot equal 0. So our restriction is that the denominator cannot equal 0. That's the only requirement that this function has. Our second function, g of x, has a square root. And so the square root, the input, cannot be negative. So let's look. The input is x squared times x squared minus 5. To not be negative means it has to be greater than or equal to 0. That's the restriction for g of x. Finally, my third example, h of x. This function involves both division and a square root. And so for the division, we are not allowed to divide by 0. And so we create a restriction that 2 minus the square root of x plus 2, that's everything in the denominator, cannot equal 0. And we have a second restriction that the input of the square root, and here the input is x plus 2 must be greater than or equal to 0. And so those are the restrictions that define the domains of my functions. If I want to find the domain, I need to solve these systems of inequalities. Our first function, f of x, had the single restriction that the denominator could not equal 0. So we will solve this inequality by starting with the equation, the equality, and ask, when does x plus 3 times x minus 4 equal 0? See, we usually start solving inequalities by solving the corresponding equation. A product equals 0 only if one or the other factors equal 0. And so I get two solutions to the equation that x equals negative 3 and x equals 4. Now this is the complement of my domain. Those are the 2 points that are not in the domain. So my domain is a set of all numbers, I'll draw a number line, other than negative 3, that's not in the domain, and 4 is not in the domain. And so my domain solves the inequality will be the set of all numbers other than negative 3 and 4. And I write that the domain of my function is equal to the union of the intervals that we've identified. So I have the interval negative infinity to negative 3, union the interval negative 3 to 4, union our final interval 4 to infinity, and I'm not including any of the endpoints. Those happen to be the points that would cause me to be dividing by 0. Our second function, g of x, had a square root, and so we created the inequality where the input of the square root, which is the formula x squared times x squared minus 5, has to be greater than or equal to 0. So this inequality is looking for positive values or 0 inside of the square root. Quick note, notice I did not create an inequality with the square root. I took an inequality of what's inside of the square root. How do I do this? I'm going to solve this inequality by sign analysis. I start by solving the equation. X squared times x squared minus 5 equals 0. And I get two possibilities, either x squared equals 0 or x squared minus 5 equals 0. X squared is 0 when x is 0, and I solve x squared minus 5 equals 0 by isolating the x, and I get plus and minus the square root of 5. So these are the points through sign analysis where my formula can change sign. And so I'm going to create a number line for my sign analysis where I indicate these values. At 0, my formula equals 0. At plus square root of 5, my formula equals 0. And minus square root of 5, my formula equals 0. And the formula that I'm talking about is the input to the square root. Notice it's not actually the function. It's not g of x. It's the input. Well, with those 3 points, I can now do my sign analysis. I'm going to pick values in each interval. I'll substitute them into the formula and see what sign I get out. So, for example, square root of 5 is between 2 and 3. So, like if I pick negative 3 and I substitute it in, I'll get negative 3 squared is positive times negative 3 squared is 9. 9 minus 5 is positive. And so I get a positive value on that interval. If I now look at a number in between negative square root 5 and 0, like negative 1, squaring negative 1 is still positive, but x squared with negative 1 is now 1. 1 minus 5 will be negative, and multiplying those I get a negative value out. So as I try additional values, 1 will give me the same signs that we just did, and if I do something like 3 on the far right, the signs go back to positive. So this gives me my sign analysis summary. I find the domain by interpreting this sign analysis, and the domain requires that my input is greater than or equal to 0. I need to exclude, I will not include the intervals where my function is negative. Alright, so let's create a set, we'll draw it below our number line, where we're going to include all the values of x where I get a positive or 0. So I'm going to fill in this point at negative root 5. Notice there's an isolated point at 0 all by itself, where it's 0, and at square root of 5, and all values to the right. And so this set, this is the domain where the input, x squared times x squared minus 5, is greater than or equal to 0. The domain of my function is now this set. And so I'll write that the domain of G is equal to the set that we found, the union of an interval negative infinity to negative root 5. I include the endpoint. An isolated point is a single set with a single number, and then union root 5 to infinity, including root 5. Our third and final example was this function that had two issues. We were dividing, and so I had a requirement that I cannot divide by 0, and inside that denominator I had a square root, and so the input, x plus 2, has to be greater than or equal to 0. So as I solve these, I need to satisfy both restrictions. The inequality x plus 2 is greater than or equal to 0, we can solve by isolating our x. X plus 2 is greater than or equal to 0 means x is greater than or equal to negative 2. And so on a number line, here's negative 2. To meet that requirement, I have to be to the right. So this is this requirement that x plus 2 has to be greater than or equal to 0. My second question is that 2 minus the square root of x plus 2 cannot equal 0. And so we're going to solve this by solving the equation, and then we'll exclude any points we find. Notice that this equation only has a single x right here, so we're going to try to isolate that x by moving things to the other side of the equation. So I might move the negative 2, I might move the 2 away by subtracting 2 to both sides. So negative square root equals negative 2. I can change the sign of both sides. Now I need to eliminate the square root. The inverse operation of a square root is to square both sides. So square root squared is now going to equal 4, and that leaves x plus 2 equals 4. Subtract 2, x equals 2. And so this is the point that's not in the domain. And so we need to go to our set, and our second requirement is that we cannot equal 2. So here's 2, and the second requirement cannot equal 2. So here x cannot equal 2. We want to satisfy both requirements, and so I'm going to be looking for the intersection of these two sets. And the intersection, both requirements are satisfied at negative 2. They're not both satisfied at 2, but all values to the right. This is my domain. And so I describe the domain by writing it down. The domain of H is the interval negative 2 to 2. I include negative 2 but not 2, and then union 2 to infinity. So you can see that what we've done is we've gone from negative 2 to infinity, and I've removed negative 2 from that set.